Hello, I'm Betty Young, a professor of physics at Santa Clara University, and I wanted to share with you a little bit of information about our program. So I made some slides and put together what I hope is a short presentation. And remember, you have the power. You can push fast forward on this at any time. So let me go ahead and share my screen and get started here. Hopefully you can see that. First up, I wanted to just give you a feel for some of the people in our department. So on this slide, I have just some favorite snapshots from events that we've done in very recent months or years, last year or two. Students, faculty, staff. It's a fun group. We all get along well together. We do a lot. There's always a lot of smiles. So let me go ahead and say a little bit about the program in particular. First of all, we offer two different Bachelor of Science degrees in our department. We offer the engineering physics degree and we offer a physics degree. They're both, again, Bachelor of Science degrees. And I'm going to say a little bit more about each of those programs in a moment. And then for the rest of this small presentation, I'll talk a little bit more about the focus we have on students and what our faculty and staff do and how we involve our students in our daily work. And then I'll just wrap it up at the end. So in our department, again, we have two different Bachelor of Science degrees. And the physics major on the left there actually has two different tracks. We have a traditional physics track, which is what most of our students take who are in the physics major. And that's a very deep and rich and broad physics program that gives students all of the traditional coursework that one would have at any great university. And we have, for example, a full year of quantum mechanics, that's 3/4, and 3/4 of electricity and magnetism. We have computational methods, thermal and statistical physics, and comprehensive advanced lab course, electronics, astrophysics, cosmology, just a host of different courses. I don't know if I said solid state already. We have a number of great courses at the upper division level that allow our students to really get deep into the heart of their studies. In the biophysics track of the physics program, this track contains the bulk of the physics major, but in addition, it's a very full major. In the bulk of the physics major, in addition to that, there are a host of courses in biology and chemistry, and those courses are in there specifically so that students that are interested in taking their physics degree and going on to medical school, for example, or maybe working in biotech, or going into graduate school in an area other than straight physics, they will be very well prepared for that. And so I encourage you to have a look at both the physics track and the biophysics track if you're interested in studying with us. About half of our majors, it depends, sometimes it's a quarter of them, sometimes it's 60% or roughly half. It fluctuates between physics and engineering physics, but a number of our students choose the engineering physics major. And here again, the focus is on physics, and so the base coursework is the core of the physics major. But instead of having quite as many upper division courses in the major, for engineering physicists, the students work with faculty advisors to choose a selection of 9 additional courses, which include engineering and applied sciences courses for breadth, and then a deep dive into a particular area within engineering, or computer engineering, electrical engineering, mechanical engineering, etc., that allows those students to go a little bit deeper into that area and prepare them for perhaps a graduate program within engineering, or to work in industry directly and have many more of those skills that they might need right off the bat, beyond the deep intellectual theoretical side of the physics major. So there's a lot more to say about these programs, but again, I was trying to keep this short, so I'll go ahead and move on for now. The physics department is part of the new initiative where we will be moving into a beautiful new campus on the Santa Clara main campus. And this is the Sobrato Campus for Discovery and Innovation. We'll be sharing this building with several other departments in STEM. There's nice aspects to that. What I can say is that the building rendition that's shown here is really what it looks like, minus the people. The building has come along very well in construction, and the outside is done, and the inside is being sort of fitted right now with all of the furniture and the walls and the utilities, etc. And so we really are on track, and we plan to open for the real deal in the fall of 2021. I am looking forward to that. I think many of us are looking forward to that. We'll have brand new classrooms and labs and offices and meeting spaces. And I think that the group of you students coming in this coming fall will have a great opportunity to just learn in a wonderful new environment. Well, once you're at Santa Clara in our department, you'll be taking some, of course, lower division physics labs. The first courses that you take in our department would be the introductory physics with calculus sequence. And each of those 4 courses, spanning traditional classical physics up through modern physics, relativity, a host of other topics, those 4 foundational courses also have laboratories. And those labs are taken very seriously at Santa Clara. We have 2 full-time dedicated physicists who have designed and who prepare the labs with an eye towards the students. So what do we really want to help students learn in these courses, and how can we do that best? And so all of the photos here are taken from our labs. Across the top there, you can see a nice electron beam spiraling in the presence of electromagnetic fields. We have nice diffraction gratings, an optics experiment where you effectively cloak or hide the object that you're looking at using some tricky optics. And also on this slide are the 2 physicists who have made so much of this possible, Dr. Omid Ahmadi-Georgi and Dr. Roxana Flacao. And another aspect of our laboratories, which is also true in our college at Santa Clara in other sciences, is that the people who teach our lab courses, our lower division labs, are faculty. We don't have graduate students, so we don't have TAs who teach the labs. The labs are taught by us, and that allows us to really interact with students closely, see strengths and weaknesses, help students build on strengths and maybe overcome weaknesses. And so that at the end of each laboratory course, the students come out, we hope, with a better set of skills, better ways of thinking about the scientific method, and being able to really perform in their chosen area. So we have a lot of fun in the lab, lots of great experiments. The 10-week quarter goes by fast, and we always try to include in there 8 or 9 really fun experiments along the way for each of these courses. Okay, so that's the big picture. Just a couple quick comments. We're student focused. We're very student focused at Santa Clara, especially in the physics department. And what I would say, and I think our students would agree with, is that we do expect a lot. We expect hard work from our students, but we as a faculty and staff are very much there to support and guide students along the way. Our doors are open. Faculty and staff and students interact daily. We encourage questions of all types. I think the students will see a refreshing atmosphere where the faculty ask each other questions, and whether you have a given advisor who's your official advisor, or whether you go to that person for your advice, or you just pop into the office of any other faculty member or staff member, you'll always be welcome. And so I think that is the climate we have, and I would hope that, well, there's no reason that wouldn't continue. So a couple slides here just to show you some of what our students do. Our physics majors, and by that I mean physics and engineering physics majors, it's all sort of the same group, and there's probably 50 or 60 students altogether over the 4 years at any one time. What's nice is that we have 2 student groups, the Society of Physics students and the Women in Physics group. And in essence, these groups are one and the same in many ways, and they're active. And the students do all sorts of fun things every year. They simply come up with ideas they want, and we support those ideas, and we play along whenever we're invited. So the students have gone on tours, spend the day in San Francisco, go to nearby tours, places like SLAC or NASA Ames, the various labs that are around us or industry. We also have events that include mentoring events, structured mentoring events, where we bring back recent graduates and not so recent graduates and have them speak with students about their experiences, both as students and then as what they experienced when they left Santa Clara, and to give advice. And we do this without the faculty present so that the students can really get and ask questions that they really want to ask, okay? And it's I think, a good addition to our program. We have student speakers who, current speakers or former students who come and give technical talks to the student clubs. And we have a journal club, which is a mix of faculty and students. The students choose the papers, and all of us who are interested get together and just chat about the physics in those papers. We do liquid nitrogen ice cream every year. If you haven't had it, you gotta try it, it's wonderful. Pizza and game nights, those are very popular with students. Students organize and have competitions amongst themselves, a trivia night, Jeopardy. Jeopardy is a famous one that's been really popular. Physics Jeopardy, if, again, you enjoy it if you ever try it. Students also have, pizza and game nights, movie nights, where they take over a lecture hall and show first run movies or second run movies. It's a lot of fun. And we have events, again, student organized dinners and student faculty dinners, and things like building batteries out of pumpkins. That's always fun. Let's see, we did that last year. Anyway, the list goes on and on and on, and I've already said a little bit too much here, so let me continue. It's not all fun and games. Some of it is just fun and physics, and we send a large number of our students attend or speak at conferences each year. Some of those conferences are local, and many of those conferences are off campus as well. And this is just a little snapshot of some of our student groups with some of their faculty mentors who have attended conferences just in the last year or two. And again, there's so much more to say about this, but in the interest of time, I'll move on. I will add one thing, and that is that our students, the majority of our students do some sort of research or internship while they're an undergraduate. And the faculty and staff work very hard to see to it that the students who are interested in doing work like this, and it's most students, have that opportunity. And oftentimes, again, that leads to publications with faculty. It also leads to really great interactions that can be overseas. We take students with us, maybe on collaborative research trips, and also to conferences, overseas conferences. And it's a lot of fun to bring research students overseas or not overseas, just somewhere else beyond the bubble of Santa Clara, and get to have them experience the wonderful nature of physics in that environment while they're still undergraduates. Okay, so let me just say in the last few minutes a little bit about the faculty and staff that are in our department and how we interact with our students. And in that sense, again, what I want to come back to is that students tend to just freely work and come between the various faculty all the time. So you can pop into someone's office and ask questions. And most of our students who want to do research, again, I should say all of our students who want to do research or internships, we find a way to help make that happen. Many of those students choose to work with faculty who are on campus. And so let me just say a brief few words about a little bit of the work done in these faculty groups with students. And so I'll flip through these rather quickly. There's so much physics to talk about, but again, I need to keep this short. So I would encourage you to look at these slides after and go online and maybe look at the faculty and the publications that they put out with their students. So in astronomy and astrophysics, we have a very active experimentalist, Dr. Kristen Kulas, who has involved a number of students in her just 5 or 6 years here at Santa Clara. Several of these students have continued on to graduate programs, work in national labs, or just go on to other opportunities. That is where they wanted to be. And her work spans everything from looking at interstellar dust clouds and the physics of light polarization as it moves through these clouds, to a host of other areas. And she's very accomplished. And again, rather than going into the detail here, I encourage you to look at her website and some of her papers and some of the work she's done with students as well. We have two highly accomplished experimental physicists who do benchtop optics. And one of them is Dr. Bachana Lumzadze, who joined our faculty just a few years ago. I think he's in his third year. And he's pictured there with two of his students who were highly involved in his research, and in fact have been on research papers already. And what he works on is very fast optics, looking at dual combs, multiple optical frequency combs, to do some really phenomenal physics and look at atomic molecular systems. He can explain to you all of the details there. The image there on the right-hand side of the screen is just an artist rendition of sort of the physics behind how his physics works. And in the middle of the screen here, I'm showing a plaque, and that plaque is a new plaque. It's a plaque that shows the patent that Dr. Lumzadze has earned for this technique. He invented a technique, this dual comb spectroscopy, which is now ubiquitous in the field. And it is an extremely powerful technique, and he is a main player in that field. And the fact that he's at Santa Clara, like all of our faculty here, I think is really wonderful. He could be anywhere, like the rest of us. He chose to be at Santa Clara to work with undergraduates and to really have his own lab where he could still be the one that's tinkering with the knobs and getting the physics. So highly accomplished, highly active, and great at working with undergraduates. We have another wonderful benchtop experimentalist who does optics, Dr. Chris Weber. Again, I'm not going to go into all the details of his work either. What I will say is that his research is just, to me, it's just fantastic. So he looks at sort of the microscopic physics of what goes on inside of materials, and he tries to understand how to understand and control the behavior of these materials. So he looks at electrons, and he looks at phonons, lattice vibrations, and he uses optics to really study at that fundamental level how quantum mechanics sort of rules the motion and the performance of materials. Some of you have likely heard of some of the buzzwords in our field, spintronic materials and topological insulators and those sorts of things. He works on those, and he's at the forefront of that field. So he regularly takes on a number of undergraduate students in his lab. He has taken them overseas many times to different facilities beyond his own very solid lab on campus. And that allows his students to both get a flavor of research beyond the scope of campus, but also to work in facilities with state-of-the-art instruments that only exist in a few places on this globe. Matthew Kim, one of his recent students, is shown there on the slide just as an example of a student who traveled with Chris overseas to do some great work. And I think the students have been very productive in his group, have a number of publications, and again have gone on to wonderful post-Santa Clara positions in industry, in graduate school, and elsewhere. Professor Ramon Guy is our resident theorist, and he works on quantum computation-related theory. So here is a place I really won't go into detail, in large part because I'm not capable of going into detail on it right now, but he does a lot of computational work and analytic work on understanding the dynamics within materials that can be used or could be used for quantum computation. So for people who are trying to build quantum computers, of course, at the foundational level, it's all about understanding the quantum mechanics and the interactions between what would become the little pieces of information in those materials. And so he simulates and studies systems, physical systems that that would be used for quantum computing. And this is based on, of course, fundamentals of quantum mechanics. And he looks at decoherence methods and mechanisms, which really would be the mechanisms that could destroy the transport or the storage of the information in these systems. And so that's right there at the, right on the cusp of what's so important in the future of quantum computation and quantum information. What's amazing to me in part is that he, again, very highly accomplished in his field. It's a very theoretical field, and yet he involves undergraduates in his research regularly. And even perhaps more impressively is that he publishes real results in top-tier journals along with undergraduates. So he's a wonderful person, and he would be a great mentor to any of you who are maybe a little bit more theoretically inclined and are interested in sort of this area. Dr. Barber, Rich Barber, is a trained condensed matter physicist who has branched out quite a bit, and I have a lot to say about his work. Again, in the interest of time, I'll keep it brief. Dr. Barber's group does some fundamental physics in scanning tunneling spectroscopy. He does this collaboratively with the group at San Diego, and he does a lot of work on campus with groups in chemistry, biochemistry, and biology, looking at the physics behind some of the structures and the functionality of the things that they are also interested in. So silk, how the web spinners produce silk that has tremendously just surprising properties, and he studies those properties in the context of the functionality. And organic solar cells, he's done work with chemists and biochemists on the Santa Clara campus to look at some novel organic solar cell types, and that work has also led to publications with students. He's working right now in part with a startup company that he's consulting on with students. So he has some of his Santa Clara students involved in this as well. And they're working on next generation batteries, some very interesting work. In that area, I really can't say much. There's non-disclosure agreements, so he hasn't even told us, the rest of the faculty, about the details of that work. But the students that he's working with also sign NDAs, and they seem to be very happy working in that environment as well. So John Balmingham, Professor Balmingham, is a trained condensed matter physicist who then did a postdoc in biophysics. And his work is just, it's fascinating to me, knowing nothing about it really, but it's fascinating what I've learned from him. So he studies how information is transported through neurons. And he uses crabs as his system, the biological system. And somehow he and his students somehow can actually inject information into one end of a neuron and watch how the sensory neurons encode that information and send it out to have for motor control within the crab network, right, the nervous system. I don't know, it's fantastic to me to be able to control at that level some biological systems, and most importantly to study what he does is sort of the computational side of things. He studies the information transport through these neurons, and he looks at this as how that information is encoded in information spikes and signals, and the rate of these spikes and the shape of these and all these other details get really to the fundamental physics of information transfer. I didn't say that very well, so you're going to want to go and talk to him about it, but it really is neat, just using biological systems to study information transfer at the fundamental level of entropy and energy and things like that. And my group, I'm a condensed matter physicist. I do a lot of work in semiconductors and superconductors. I work with a few large collaborations right now. I also have done a number of independent projects over the years. And here I've just shown some of my students who have gone on, and it's been wonderful to work with them. They're all Santa Clara students, and what I always tell them, and all the other students that come to our program and are interested in doing science and physics and engineering physics, you know, when they're trying to figure out what to do, what I love about our department is we have a large group of faculty who are highly active in research, all of us working with our undergraduates. And as I tell my students, like Dr. Seuss says, you have brains in your head, you have feet in your shoes, you can steer yourself any direction you choose. And to me, that means, you know, really think about what it is you want to do, not just with your college career, but beyond. And we at Santa Clara are here to help make that happen. We want to help you grow. We want to help you learn. My students have gone on to universities for graduate school, great university programs. They've gone into industry. They've gone to national labs. They've gone a variety of different places, startup companies. Some of them have started their own startup companies. It's all good. We support it all. And we love to see where our students go. So to finish up here, I have spoken more than I had intended to. Maybe you've used your fast forward button. What I'd say is, again, we have what we think are very successful and fulfilled graduates, graduating about a dozen students a year, sometimes 16 or 17, sometimes 8 or 10. It all depends on the year. About half tend to be engineering physics and half physics. Again, that varies from year to year. It might be 2/3 physics, 1/3 engineering physics, or what have you. Probably about half of our students overall go on to do some sort of graduate degree, most or many in a PhD program in physics or engineering, but many in math or applied math, medicine, law school, business school, applied physics, and then you know, about half go into teaching or technology, R&D, working in national labs, working in industry, starting companies, and on and on and on. I want to finish up, though, with just a snapshot of our recent graduates. These are just great people, and I love to see their smiles. I'd like to think that this photo, which was taken, unfortunately, via Zoom because of the COVID-19 graduation that was done online, their smiles, I think, are genuine. I hope they're genuine. Our smiles for them certainly are. And they're all off and running with their careers in a variety of ways. So just a great group of students. And, you know, we would hope that you would possibly want to be one of the next crop that's coming through as well. So let me finish up and just say that I'm open to any questions at any time, as are the faculty and staff in our department. You should feel free at any time to reach out to us. Email is probably the easiest these days because we're running around from place to place, but you should not hesitate to reach out and talk to us. Again, I just want to finish up with one final comment to you if you're thinking about coming to Santa Clara for an education. I really feel strongly about this, and I want to say right up front, physics at Santa Clara is a great program. I think that we have a great environment. We love our students. I think faculty and staff and students get along quite well. In my heart of hearts, I know that choosing a college is a very difficult step, and it's a scary step. And I really want you to do what's best for you. If you find a program that you think is better than ours for your specific needs or goals, that's great. You know, you should do what's best for you. I do hope you look at us. I think we have a great program. We would love to have you. We would love to answer your questions. But most of all, I really want you to have a great experience, and I wish you well, and I hope you stay safe. I hope to see you at Santa Clara, and don't hesitate to reach out and ask us about physics or engineering physics. Bye for now.